this lesson is about significant figures, and sometimes the term itself can be confusing, so let's just start by talking about what it means to be significant and, frankly, what a figure is. Figures first. So a figure, another word that you could use for a figure, is simply a digit. In fact, some people refer to this idea as significant digits. Now, significant in this case means it's representative of something. In other words, it's meaningful. Now, in the terms of quantifiable measurements that we might make in the world of physics, that means if we've made a measurement and we include a number, any digit, in that measurement, that measurement actually represents something meaningful. It's not just a wild guess. It's not something that the tool told us exists, but it didn't really measure. It's a more accurate measurement if we've got more digits. So let's take some motion that you'll be very interested in November. We're going to be going outside and launching water balloons, and you get to shoot a water balloon at your teacher. Let me show you a video of that launch and what it looks like. So hopefully it's a nice blue day like this one was. We're going to zoom in just a little bit and look at the motion. Excuse the pan there for a second. I'm going to put this off to the side. All right, so the video that we took here, you can see this is Mr. Lowry here, and this is our large water balloon launcher. It's basically a huge slingshot. So let's push play and you can see what happens. So he's holding it, fires it, the water balloon's released, it flies through the air, and right about there you can see a splash. Now, if we were to measure the time in the air, which actually ends up being very important to this lab, with just a clock on the wall, we might not be able to measure it as accurately as we need to. In fact, I know we can't. So let's push play and just estimate using the second hand on the wall. From launch, right there, 1 1000, 2 1000, 3 1000, and there's my splash. And if we try and do it again, since it's on video, we can do it more than once. So right, 1 1000, 2 1000, 3 1000, 4. All right, and I counted on 1 to 4, so that was 3 seconds. Do it again. Fire. 0, 1, 2, 3, and it hits. So if all we're using is the clock on the wall, really all we can get to is this takes about 3 seconds. We would consider that to be one significant digit. In other words, we have only the 3. We have no idea how many tenths of seconds, or how many, certainly not how many hundredths of seconds. So let's zoom out a little bit here, and let's think about using something to measure the time that allows us to measure it more accurately, i.e. a stopwatch. So we're limited by, you see up here what it says from here to here. When you or somebody else uses a tool to measure something, we're limited by the accuracy of that tool. The clock on the wall can really only measure 2 full seconds. Estimating in between the seconds is not possible. But with a stopwatch, of course, we should be able to time this a little bit more accurately. So let's bring in this motion again, and this time we'll bring in a stopwatch. Sorry about the glare on it there. And let's do this a couple of times and maybe average them together. So if we hit start, I'm going to try and start the stopwatch when it leaves, right there, and then when I see the splash, right there. So I got 2.82 seconds. Let's try it again. Careful when you're making those S's so they don't look like 5s. So we'll reset this and push play again. Fire. Trying to start it when the water balloon leaves to when I see the splash, and I got 2.90 seconds that time. Let's do it again. Fire. 2.87 seconds. And one more time. 2.85 seconds. Now, you can see that we have a little bit more accuracy and precision than we did with the clock on the wall. We know that it's not quite 3 seconds. What we're consistently getting is 2.9 at a high, 2.82 at the bottom. We could do this more than 4 times. We could have multiple people do it, average that data together, and we might be able to come up with as many as 3 sig figs, but certainly 2. So because we are getting consistently 2 seconds, and there's some variation at the tenths place. Some of my trials have showed that it's a little less than 2.9 seconds. One of my trials shows that it's 2.90 seconds. The more we did this, the more we'd see how much the numbers, where the numbers are varying. This digit appears to be a little random. If that digit is random, even though the stopwatch displays that digit, we're not actually measuring that accurately. So if I averaged all these together, I would get 2.8 something seconds. If it were more than 2.85, I'd round up. So let's do some quick math in my head. 0.2, that'd be 0.9. If we add all this up, we've got 4 and a carry of 1, 24, 25, so it'd be 34.3 here. 11.44. If we divide 4 into 11.44, what are we going to get? We get 2.86 as the average. Now, it would be good lab procedure to do this more than just 4 times, but for purposes of understanding significant figures, what we need to realize is that we would round that to 2.9 seconds because that digit, the 6, rounds the next digit up, and we're only going to keep 2 digits because the 3rd digit appeared to be random. And the more trials we did, the more we'd be able to see if that 3rd digit is in fact random. And if it is, then this method only gives us 2 significant figures. Now, one important thing about that is whatever we calculate with this time, we would only be able to keep 2 digits in what we calculated. In other words, we have less accuracy than if we could keep 3 significant figures. Now, some of you may have noticed that this is time-stamped. So the reason, in fact, that I took the video in this app is so that I could use the timestamps rather than using a stopwatch or a clock on the wall. So let me show you how we actually take the times for the lab. We'll zoom in again so you can see it a little bit more clearly. And because there's a timestamp here, sorry for the refocus, if we can find the frame where the water balloon leaves, there it is right there. It's pretty cool to watch in slow motion. As soon as it's not in contact with the launcher, which is right in that frame right there, that's at 2.71 seconds. So that's the time when the trajectory begins. I'll write that down off to the side. And then we can look for the splash. And the moment we see the splash, there's the water balloon right there, just a little dot. We see the splash right there at 5.48 seconds. It's round, it's flat. 5.48 seconds. If we take those 2 data points and we subtract them, 5.48 minus 2.71, we get a time of, between those, 2.77 seconds. Now that time has 3 significant figures. I'm able to, in the video, see to the hundredths of a second when events are occurring. And even though that's fundamentally different than the 2.86 seconds we found with the stopwatch, it is more accurate because we're using a better tool and we're using it in a better way. The stopwatch is, of course, affected by my perception of when the trajectory began and ended. I'm having to watch it and time it in real time, and my reaction time with my finger or my thumb affects the measurement, whereas on the video I can watch it and freeze frame it. So we actually will video quite a lot of motion because it's useful. Now, let's talk about a different example. Say we're not measuring distance, we're measuring length, or excuse me, we're not measuring time, we're measuring distance. So we have different measuring sticks that have different gradations on them. Let me show you some. So this is a stick that's about 1 meter long. Here's the beginning of it. You can see that it's got no marks on it. As I move it all the way through, there's my hand. There's the end. Well, that's a stick that's about 1 meter long. Not all that useful. Good for estimating, but not for much accuracy. Now this is what we call a photographic ruler, and you can see on the photographic ruler that we've got that 10 is 10 centimeters. The marks in between then, the larger marks are individual centimeters and the smaller marks are half centimeters. So we've got some finer lines on there. We can measure more accurately with this. Now our most accurate meter stick looks like this, and that meter stick you can see has even finer marks. It's inches on top and centimeters on the bottom. These are inches. We don't want to use those. This is just some tape that somebody stuck to this once upon a time. This is 42 centimeters, 43 centimeters, and these individual marks are individual millimeters. So this has marks that are 5 times closer together. We can make much more accurate measurements with something like that. So if we were trying to measure the width of a table, or the width of a table, excuse me, the pan here. I'm gonna move out and take a look at that table right there. There we go. If we are trying to figure out how long that table is, which might be important if we're rolling something across it, you can see that if we take the stick that's just about 1 meter long, we could line it up with one edge, and you can see that it's a little longer than that. I can kind of put my finger there and move it down, and it goes to right there. If I look at that, that's maybe 6/10 of a meter. So maybe I could come up with this is about 1.6 meters. Whereas if I use the photographic ruler has finer marks on it. So there's my meter. And what I actually see is that I overestimated a little bit. It's actually at, I'll keep my thumb there, and we'll move over so you can see it together. It's actually only at about 53 centimeters. So it's really more like 1.53 centimeters. So again, 1.6 compared to 1.53. 1.6 has 2 digits. 1.53 has 3 digits. When we talk about significant figures, we mean that we've actually measured those digits. So if we're trying to measure the width of a table, and we have a stick that's about 1 meter long, we're able to estimate this digit. It's meaningful because it's close. We're able to estimate it. We can keep it. The photographic meter stick gave us 1.53 meters. That is 3 significant digits where this is only 2. And so we've made a better measurement. Now we can't just tack on more numbers than we really know. Now frankly, even though the meter stick has marks that are even closer together, if we have to move the meter stick, we can't get as good of data because when we move it, we've changed where 0 is. We would need a measuring tape with millimeter marks on it, and then we could get 4 or maybe even 5 significant figures about how wide the desk is. So sometimes you don't need very many significant figures. It's okay to make an estimate, but if you need an accurate measurement, you have to use the right tool and then report that measurement with the right amount of digits, because the amount of significant figures you report reflects how accurate that value is, whatever that value is, be it time in the air or the width of a table. Now, let's go to the second slide of the notes. The second slide of the notes talks about what to do when we are calculating using significant figures. So, oftentimes in physics, we will measure 2 or 3 things and use those 2 measurements to calculate something else. So here's a simple one. If we make a measurement very accurately, we'd have to have very good measuring tape, use good procedure, and we measured that something moved 4.1129 meters. Recognize that's centimeters. This is millimeters. This is actually 9/10 of a millimeter. So we're talking about a very, very fine measurement. But we only used a stopwatch to time it, so we only have 2 digits, so we've got 3.3 seconds. If you plug that into your calculator produces 1.2463 forever meters per second. The key in making good measurements is recognizing what ends up happening if you have a poor one. this is only 2 significant figures, while this value has 5 significant figures. But every calculation is only as accurate as its least accurate measurement. Since this only has 2 significant figures, we would need to round this answer of 1.246 to 1.2. A note on that, since this is 1.246, we don't serially round. If we're going to round at 2 digits, the 1 and the 2 are both significant, we just look at the next digit only. It's a 4, so we just cut it off. If the next digit had been 5 or greater, we would have rounded this 2 in the 10th place up to 3. So, let's say you had 4 givens, and 3 of them have 5 sig figs, and 1 of them only has 3 sig figs. You'd round your answer to 3 sig figs, because again, the accuracy of anything you calculate is limited by the least accurate measurement that you start with. That's why it's so important to make every measurement a good one. One poor measurement affects the rest of the calculation that we will eventually be doing. Now, finally, these rules are posted in class, and for quite a while you can use these rules when you are considering how many digits to write down and how many significant figures are in a number that is already written down. The trouble comes with zeros. All non-zero digits, in other words, if you see 1 through 9 in a number, that number would only be written if it was measured or reasonably estimated. In other words, if it's written down, it's a significant figure. It also means if you write a 1, 2, 3, 4, 5, 6, 7, 8, or 9 down, you are saying that you measured that or reasonably estimated it. The trouble comes with zeros. You can see rules 2 through 4 are all about whether a zero is significant or not. The trouble can be that a zero can act as a placeholder, but it can also be that you measured that thing and there just didn't happen to be any. It's significant if it was measured and there wasn't any of that in that place. It is insignificant if it's just a placeholder. These rules help you to recognize which zeros are significant or not. So zeros in between non-zero digits are significant. In other words, these 2 zeros are between 2 ones. The ones are always significant. We wouldn't write them if they weren't measured. That means that this number, 1001, has 4 significant figures. And so if we were to use it in a calculation, as long as all the other values also had 4 sig figs, we could keep 4 digits in our answer. Now, this also has 2 zeros in between non-zeros, so this also has 4 significant figures. Now, leading zeros are never significant. They are just placeholders. So when we look at a number like 0.00078, that is only 2 significant figures. The purpose of these zeros is just to keep the 7 in the tens, hundreds, thousands, 10,000ths place, and the 8 in the 100,000ths place. This 7 and 8 were part of an original measurement. The zeros simply quantify the value of the 7. It's not 700 or 7 million, it's 7 10,000ths. So zeros that act as placeholders like these zeros, and zeros that mark where the decimal point is like this zero, do not count in terms of the accuracy of the measurement. Now, trailing zeros are only significant if there's a decimal in the number. So 910 is 2 sig figs, but if we write it with a decimal like this, we are saying we measured the ones of whatever this is, and there weren't any, and to report that we put the decimal place, and now it's got 3 sig figs. If you come across a number that has like 7,003, and you need to report that with 2 sig figs, that is a unique case. It's hard to do, because if you round it 7,000 and put a dot, that would be 4 sig figs. If you keep the 3, that's 4 sig figs. And so you want a way to show that the hundreds place counts, but the tens and ones were estimates. In that case, we'd use scientific notation. 7.0 times 10 to the third. When looking at scientific notation, this moves the decimal place, so it's not part of the sig fig calculation. This has a trailing 0, which is significant if there's a decimal. So 7.0 is 2 sig figs. And what that means is you knew there was 7,000 of that thing. You knew that there was 0 hundreds of that thing. You're not sure about how many tens or ones of that thing there was. We don't expect you're going to learn sig figs in a day. This class is not about sig figs, but it is an important thing to get to learn as we go. So what we want you to do is simply practice with significant figures and take feedback as you try to round values to the correct number of digits, and to practice getting good sig figs when you're taking lab data to take it as accurately as you can. All right. Finally, if we're going to be able to converse back and forth and use significant figures, one of the keys is being able to round a value. Just like we did in the previous slide, where we figured out that the velocity calculated from the two values we had lots of digits in it, but those digits aren't meaningful because we only had 2 significant figures in one of the data points. We also need to be able to round answers to other amounts of sig figs. So we're going to practice rounding these to 3 sig figs. So 124.62. That would be 5 sig figs written that way. If we only know it to 3 places, that means we're going to keep the ones place, but we're going to cut off the tenths and the hundredths. So we're going to cut it off right here. The next digit's bigger than 5, so we would call that 125. That's as accurately as we know that value. 1001 to 3 significant figures is the same problem I was just discussing up here. If we put a decimal place, if we round it to 1,000 and put a decimal place, that's 4 sig figs. If we just call it 10, of course 10 and 1,000 don't mean the same thing, so that gets us really far from what 1001 means to 3 places of significance. What we want to say is we know the tens place is 0, but the ones place is kind of a guess. So the way we'd write that is 1.00 times 10 to the third, and again, trailing zeros are significant if there's a decimal. There's a decimal, 1.000, 3 sig figs, times 10 to the third means the 1 means 1,000, the 0 means 0 hundreds, and this 0 means 0 tens. Finally, rounding this to 3 sig figs, leading zeros are never significant. The first significant figure would be this 7. So we go to this digit here, that's 3 significant figures later, and we're going to round after that. So 0.000709, the next digit's an 8, so we're going to round up. Of course, if we round up that 9, that really turns into 0.00071. But if we leave it like that, we've got 2 significant figures. We need to add that last 0. Remember, trailing zeros are significant if there's a decimal. Leading zeros are not. So these 3 zeros are not significant, but this 0 is. Non-zero digits are always significant. This is 3 sig figs. It is okay to make mistakes with significant figures. In order of importance, start with making good measurements so that you have lots of significant figures so that our calculations can be accurate. The next priority after that is learning how to read numbers for how many significant figures they show, and the last skill that you'll learn, and it'll take a month or two, will be rounding answers to the proper number of significant figures. We're introducing this idea now simply so that you get some practice. Happy sig figging!